So this is going to be part 2 of lecture 5. I'm going to talk about heat capacity and specific heat capacity and do some calculations with this. So heat capacity is usually labeled as a capital C. It is the amount of heat absorbed per increase in temperature. So the unit you typically see for this is going to be a heat unit over a temperature unit. So another one you could see is calories per degree Celsius. Now realize heat capacity of a substance then really is going to depend upon how much of the substance you have. So the example I always give for heat capacity is if I have a beaker filled of boiling water versus a drop of boiling water. If I were to drop the beaker of boiling water on your hand versus the drop of boiling water on your hand, you would have a much different experience. And that is because the beaker of boiling water has a much higher heat capacity than the drop of water. So the issue with heat capacity is there's no mass that you can compute here or take part. So it does depend upon the mass, the heat capacity. So that is why we really look at something called the specific heat capacity. And now it's shortened to what we call specific heat. So the symbol is a CS, capital C, lowercase s. It is the amount of heat energy required to change 1 gram, 1 degree Celsius, okay? So realize that the difference between this and the previous is the fact that we're talking about per 1 gram. So the units you typically see for specific heat or specific heat capacity is going to be joules per gram degree Celsius versus or calories per gram degree Celsius, depending upon, again, what you are looking at. So for water, okay, it should be CS. Some books use S, so that's why you will sometimes see that in my notes, but your book uses CS. The specific heat of water is a very famous number, 4.18, 4.184. Joules per gram degree Celsius, or 1 calorie per gram degree Celsius. This is really how we get the definition of a calorie, is based off of water. Water's the standard for thermo for us. So how much energy does it take 1 gram of pure water to change 1 degree Celsius, 1 gram of that water? That is how we define a calorie. That's how we define a calorie. So, but you might have remembered 4.18 from first year chemistry. We used it in a lot of different calculations. And another thing you might have remembered is the equation, okay, that is extremely valuable when we are working these calculations. So Q is equal to MC delta T, okay? Q is equal to MC delta T. So what exactly does that stand for? Well, Q is going to be heat. M is mass, then we have specific heat, and then we have the change in temperature. So if we are doing these types of calculations, heat could be in joules or calories, but I'm going to keep it in joules because that's the most common one. Mass is going to be in grams. Specific heat is going to be joules per gram degrees Celsius. And my change in temperature is going to be degrees Celsius. So here again, we don't need to change anything to Kelvin. We just are looking at, from the beginning and the end of the experiment, what is the change in temperature. So I like to show the units because the units all cancel out. So grams cancel grams and degrees Celsius cancel degrees Celsius, and you're left with joules. So again, change in temperature is going to always be what we call final minus initial. So make sure you have that in your notes. And Q again is going to be negative or positive. Now again, we will talk more specifically about what does the sign mean for my delta T versus my Q. But this is where Q is going to be either negative or positive, and that's going to determine exo and endothermic. So let's try a problem, and we'll kind of derive how we're going to kind of approach some of these things. So we have a 50-gram piece of iron at about 90 degrees Celsius. It is placed in 100 mils of water at 10 degrees Celsius. What is the final temperature of the water if I have my specific heat of iron being 0.52 joules per gram degrees Celsius? All right, so this is what we call a heat transfer problem. Heat transfer, and that is because we are essentially transferring that piece of iron to that water. So any of the heat that was in that iron is then going to be put into that amount of water. So I'm going to say Fe is transferring to that water any amount of heat. Okay. Now we are going to assume there is no heat lost to the surroundings. Okay, so no heat loss to the surroundings. So if that's the case, I can then set two things equal, the iron and the water. Okay, so I could actually look at, okay, I have some information about the iron. I have the 50 grams, I have the change in temperature, and I have its specific heat. Water, I know how much water I have. I know its starting point. I don't know the final temperature, but I could figure that out. So anytime we're doing these types of problems, we're going to set energy loss to energy gained and make it equal. Okay. So again, we're going to assume that there's no loss to the surroundings. That is a source of error, and that is something you could discuss when we're doing labs, and having a discussion of labs is going to be a component of this. But because the energy is being lost, we're going to put this side as negative, and this side is going to be positive. And that will fix a problem we have with delta T, because our delta T's is always final minus initial, final minus initial. So that's going to play a role in here as well. All right, so I'm going to use Q is equal to MC delta T for this. So I'm going to take 50 grams of my iron, okay, multiply it by its specific heat. And then I have its final temperature minus its initial temperature. Well, I don't know its final temperature, but I know its initial temperature is 90, okay? Then I'm going to make that equal to the water. Well, I know water is 100 milliliters. I'm going to assume that it is at a density of 1 gram per 1 milliliter. So I'm going to put 100 grams. And again, I would give you that idea if otherwise not stated. And then the specific heat of water is 4.184. I should probably write the 4 in there. And then my final temperature of the water is exactly the same as the iron, because again, it is going into the same place. And so, but the initial temperature of the water was 10 degrees. So I mistakenly wrote 100 there. So please disregard that. So energy is being lost, okay? So if I take my hot piece of iron, at the end, once I have dumped it into water, is the X value here for the iron going to be higher or lower than 90? It's going to be lower than 90. So the change in temperature here is going to be negative because of that. So why we are putting a negative on the other side is to essentially get rid of that negative. Over here on the water side, the temperature of the water is going to go up. This X value compared to 10 is going to be a bigger value. So you need the positive over here and the positive over here in order for it to work. So pause the video and see if you could find X. Pause the video and see if you could find X. So your calculator should have spit out 14.1 degrees Celsius, 14.1 degrees Celsius. So we are going to be looking at these heat transfer problems according to what we call calorimetry, So calorimetry, and more specifically coffee cup calorimetry, is something under what we call constant pressure. So why that fits with what we're talking about is it is open to the surroundings. So the coffee cup image is literally a styrofoam cup. The reason we use a styrofoam cup is one, it's easy accessible. Two, it's because it's somewhat insulated, so it will keep some of the heat in. So if I am looking at the previous problem that we just did, heat lost by the metal is equal to the heat gained by the water. But this coffee cup, or the calorimeter itself, also is going to absorb some heat. So I always like to mention this. This is a source of air as well. And we're not going to do really too many calculations with this. I'm just going to show you where it fits into the mold, just because the calorimeter constant doesn't always work out so good. So if I go to Q's for my symbol here, Q of metal is equal to Q of water. But if I have a calorimeter, this is going to be its constant, okay? So every coffee cup would have its own constant associated with it, and it would change depending upon how much you put in there. So the constant, the calorimeter constant here, so C cal, is going to be in joules per degree Celsius or calories per degree Celsius. And again, it's going to be more of a heat capacity than anything else. So how much heat can absorb before you start to see a change in temperature, before you start to see a change in temperature.